All right, it's 2 o'clock. So let me just get some of the housekeeping things out of the way. Give me 1 second. I need to do this. All right. All right, cool. Everything seems to be in working order. So, a few housekeeping things. This is the repository where all of the materials are going to be. Right now, if you go to the main website, it is not exactly up to date right now because I did a whole bunch of additions about 30 minutes ago. Um, but there was an error in the code that I wrote, and so I didn't catch that until about uh, 20 minutes ago. And the book, because of all of the new stuff that we're going to be covering today, um, takes about like 30 minutes to build now instead of 15. So the book right now is going to be out of date as soon as the materials that I am working with. As soon as the materials that I'm working with are built on the temporary website, I'll post that up, and then so at least if you want to follow along with the code, you can, and then just give me like a month or so to fill out the text and the prose and all the explanations and stuff. This is the first time I'm teaching this set of materials, so it's mainly trying to get the flow of everything correct. So hopefully that all works out for everyone. The other thing, if you go to this website, the main website on GitHub, again, what I want you to do, because there was a bunch of new data sets that were added, we are going to download another copy of this repository. So I'm going to click the little code button here, click on download zip, and extract this onto my desktop. Actually, I'm not going to do this on my desktop. I am going to make a new folder, and I'll call this 2021-09-28 class. Yeah, and then I'll put that in there for me. And this is the same process that we went through yesterday, getting the data sets, but I am just going to sort of say, let's just download the whole project again. None of the stuff we worked on yesterday carries over to today. None of the stuff from the part one of the workshop series is going to carry over today, other than like concepts, but at least the code topics, the things that we're going to write code wise, isn't going to be used today. So in our studio, in the top right hand corner, you can open up project, and then we can navigate to the folder that we just created. And it's really important that you actually went and unzipped this folder. That is definitely a thing to keep in mind. All right, so once we're there, we should end up with a pretty bare repository. You can see here on the right hand side, um, all the files that we worked on yesterday isn't there. I'll, in the post workshop materials, put everything into a single repository that you can download, and so all of the materials will be together. And then give me a couple of days when I get all of the video recordings from the various computers and crop the ends and then get the timestamps on YouTube, and then I'll send out a email with all of that information out there. So one of the things I want to cover today, this sort of stems off of where we left off yesterday. So this is probably the only thing that This is correct. This is probably the only part that relates to code from yesterday, but we'll try to run through all of the code, and I will very quickly go over it, and then we'll see from there. So I'm going to save a new file. I'll call this 01, and I'll call this join underscore recap. I guess that's what I'll call it. All right, so one of the things that we ended up doing yesterday was we loaded up the encounters data set, and then we joined in those different data sets, right? And so here in R, we can say library tidyverse to load out the tidyverse library. We can load up the janitor package, and remember from this was the library that we used to clean our column names. So we had our encounters data set that lives in the data folder, in the Cynthia file, and then encounters. And then when we load this up, we want to say pass this into clean underscore names to get our encounters data set. And each row in this data set is a particular encounter at a hospital for a particular patient. We can see why they were here, the description, how much that encounter cost, and then reason description. And this all comes from the project called Cynthia out of MITRE. So this is all generated data. So none of this is actually for real. All right, so where we left off yesterday, I just want to run through the code and show you where we left off yesterday when I said like, hey, I need to, I tried to like answer the question like, hey, we have encounters, we found the people that had heart attacks. So I won't go through the code bit here because there's a lot of actual code stuff that need to get typed. But this is where we left off. Oops, give me 1 second. Yeah, we left off at like age at the time of a heart attack, right? And that was the question that we had. And then to do that, we had to join the encounters data set with the patient, filter on how do we define heart attack, et cetera, et cetera. In R, if we use lubridate, that date package that handles with date, there's a function called today. So you can always find like today's date and to do your date arithmetic. And then remember yesterday, there was also this function from lubridate called YMD for year, month, date. And if we give a string that's year, month, day, it will give us the date timestamp form of that string. And why is this important? It's because computers keep track of time in number of seconds since January 1st, 1970. And so it needs to have that value, not the string, to do all of the date arithmetic. And the thing I was trying to do yesterday was, hey, I wanted to calculate this value that was like what is their birthday, like how old are they today, right? So that's going to be like the birthday in the data set minus the current date. That's how you do it. And the thing that I was having issue with yesterday that I totally forgot and it was in my notes is in lubridate, there's this special function, just like I covered, like %in%. There's this other function called %-%. And you can think of this as the function that lubridate uses to calculate date ranges. Like we would use an m dash or 2 dashes to calculate the time between these two dates. So it's %-%, to calculate the time between those two dates. And then if we want the actual, we'll see if I look at this data set here, MI encounters. If we run through this, we actually get a duration timestamp, right? Because it is a timestamp. It's saying like the duration is from here to here. But we actually want to make the calculation of turning into number of years. And this is the thing, like working with dates is one of those things where you literally go look up the guide on how to work with dates and then just sort of like figure it out, because I actually don't remember how to work with dates, because I work with dates occasionally, and when I do, it's like I have to relearn it from scratch, etc., etc. Part of this set of materials is like, okay, I finally wrote it down, so maybe that's a good thing. But just so you know, in the R4DS book that you can read online, there's literally a chapter called Dates and Times, and so you can scroll through this for a lot more detail of what's going on. But essentially, we have to say, like, here is the duration. We want to divide it by years because it's just like a timestamp, so we want to divide it by years. And then we're going to do what's known as a truncated division, because like no one really cares if you're like 34.37 years. They just care about 34. So the truncation is a built-in R function that just throws away the decimal point. And so once we have the age, that's the age today. And today is defined by the day of the when the data set was created. And so not everyone's age that got created, like where we have an age category, is valid, right? So that's another thing you want to keep track of, because if you all of a sudden say like, these are all my patients with a heart attack, and then you go and calculate the age and do a histogram on age, well, you'll notice that like some people died in this data set, right? And this is like, this person died in 1989. It is 2020 right now as far as this database is concerned. And so this age of 79 is not actually age of cardiac like heart attack, nor is this an age that like exists for that particular person. So that's one thing you need to keep track of. Like, yeah, the code is working, but you have to be very mindful that what you're doing is correct. So the other question was like, okay, we want to know how old they were at the time of a heart attack. So we can use the same percent dash dash notation with truncating divided by years, but instead of subtracting the current date, we subtract it from the start date, which is the day that they showed up in the hospital for that encounter. And we can do that difference, right? And this makes sense because there's no way their start date's going to show up before they were born. That's probably going to be a data entry error, or you flip if you get negative numbers, like you probably flip the ordering of the calculation. But we can do the same thing in that sense. So now if we look at MI encounters, we can see here age of event, and you can see like, yeah, this person is 52 years old in the database today, quote unquote today, but when they showed up to the hospital for that first heart attack case, they were 34 years old. And then once we have that information, well, then we can go through all the ggplot stuff that we covered in part 1 and a little bit yesterday as well. So we can say like, oh, here's a histogram. Oh, that's interesting. It looks bimodal. And this was that bimodal thing that I was talking about. Like, hey, there's like people above 25 and then a bunch of people around 50. We can color it in by description. So remember, there's cardiac arrest, which is general, like the heart stopped working. And then there's myocardial infarction, which is another way you can get cardiac arrest. So not every cardiac arrest is a myocardial infarction, but every myocardial infarction is a cardiac arrest, right? So they have like that kind of designation. You can get a cardiac arrest from other use cases, like a drug overdose. Your heart can stop from drug overdosing, but that doesn't mean your heart stopped from a myocardial infarction. And so we can now like take different views of this. Maybe you'll see like, hey, most of these, it looks like myocardial infarction pretty much is like pretty flat and you can get it anytime in your life, but like actual heart attacks seem to like, there's something else going on. And the way this data set is, maybe we need to explore this a little more, right? I'm not gonna go into that, but in the data folder under Cynthia, oops, not under survival, under Cynthia, maybe there's something else in here. Maybe you can look at their medications and attach medication data to the patient, because maybe, you know, did it get a heart attack because they're taking medication to manage cholesterol or whatever, or, you know, if you look at other encounters, like did they constantly come in for like other like fractured bones or something that can point to like some other reason. And so you can use that bit of information to figure that out. And the only way we could have done that is by combining two tables at once. So that was the thing that I promised yesterday that I would come back and review. And so that code will be eventually in there if the book actually properly builds. So, and I just realized I was just informed that the build is also still not working. So during the next during our first break, I will go and fix that, and it's going to take like another 30 minutes or so to go through. Okay. So today, one of the things, yeah, I know that like that script wasn't very useful, but I'm just gonna call it like this. So today, one of the things I asked you yesterday to do for homework was to go and get an API key at the US Census, right? So hopefully you got an email in there. Don't worry if you didn't. We have in here the data sets to make it up for you, but at least you can see the code running on my end. All right, so we're gonna load up a data set. So I'm gonna say library. So I'm gonna restart my R session, which is going to the session button up here, clicking restart R to restart the R session. And I am going to load up tidyverse. And we're going to load up a data set called leading causes of death. All right, so LCOD. We're going to read our read CSV data, and it should start with a capital N, and then you should see the NCHS leading cause of death, United States.csv. This is the data set that comes straight out of the CDC. And one thing you'll notice when I talked about, don't having spaces, you can see they have spaces and dashes in the file name, and it really just makes your programming life a little bit easier. And it's also nice it's coming out of the CDC like this. Another reason for this is because of it's downloaded from the internet, and spaces are also weird on the internet. So if you ever see like a %20 something in file names, it's because that's like the code for space as far as like the internet is concerned. So people just put dashes and underscores so they don't have to see all of that extra and not useful information. So if we load up this data set, we can see like for a given year, so years right now, it goes to 2017 all the way up to 1999. So like there's a bunch of years in here. There is a cause name, so we can see like there's accidents, influenza, there's a nice shorthand version of it. And then for a particular state, the number of deaths, and then an age-adjusted death rate. And so this was a data set I was originally hoping to like use as our joining example because I wanted to show how you can actually go and calculate an age-adjusted death rate. That's relevant now. It's always going to be relevant. So finding death data is actually a little bit more complicated than I expected. So instead of age-adjusted death rate, we're going to go through the process of calculating a population-adjusted death rate. It's close enough. So instead of like age groups, we'll do it by like population adjusted by state. So then we can get a sense of like, are people like how are just the overall crude death rates comparable between states, right? Because you can't exactly compare death rates out of like New York, Texas, California, like those huge population states with like Montana and Wyoming, right? There's just going to be 250,000 deaths a year in larger states compared to smaller states. So how do you compare those numbers? And that's what the adjusted rates are for. And so I'll go through the process on calculating that. So here's a small exercise I want everyone to go through. And then that should catch some people up if you have any issues, if there's stragglers coming in, et cetera, et cetera. I want you to take this leading causes of death data set, and we'll just look at 2017. That's the latest, I think that's the latest value in here. And so we'll look at 2017, and then get a list of the unique values of the causes, like what causes are being listed here, right? Because this is leading causes, so it's like the top n number of causes. I want to see what's been listed. So we'll go through that and get the values for like the all causes death counts, right? So there's different cause names in here, but we are going to pull out all causes. So let's take about a minute to go through this short exercise while I sort of settle in. Okay, let's go through this. The first part of the question was, let's filter the data set just looking at 2017. So I'll say LCOD 2017 is going to get our LCOD data set. I'm going to filter such that the year column is equal to 2017. And now you'll see that we have 572 observations with 6 variables. Next part, get the unique list of the 1 through 3 cause column. So I picked this column on purpose. So first, we want to take this data set and we want to get the unique values. So we can use distinct, and we have to pass in a column name. The problem is this is a column that has spaces in it. We didn't run clean names on purpose. So the way we do that is we use a set of backticks to identify this column. And now we can see here are all of our cases, right? So that's the reason why using clean names is helpful. It'll also fix the fact that this begins with a number. There's mixed cases going on, there's spaces. So this column has a bunch of problems in it. So that's how we can find that bit of the information. And then we'll notice that in this data set, we have accident-related deaths, all causes, like this is just everything. So I talked about crude rates and Simpson's paradox, but we'll just look at crude rates for now. Alzheimer's disease, so you can really pick whatever you want. I'm using all causes, one because it's shorter to type, and like you can see like there's all of these other codes associated with it. So instead of dealing with them, I'm just going to be using all causes. And I don't exactly know what those codes refer to. I'm assuming like it comes from an actual like formal coding system. And so I didn't look into exactly what those coding systems are, but let's go and filter our data set. Looking LCOD 2017, and then I'll call this all causes, right? So I'll just use all, and then the way we do that is we take our 2017 data, and then we use filter again. And we filter, so we have to use this quote, this like backticked column again, is equal to all causes. And remember, the capitalization and spelling is correct, matters. And so now you'll notice we have 52 observations, right? So as you're processing your data, think about what makes sense. 52, how many states there are in the United States? Well, there is 50 official states, so I expect if I click in here, they probably also counting DC, and they do. And the other one, they're also counting Puerto Rico. And I should see, oh, where is it? District of Columbia and, oh, what's the other territory that they counted? DC, so that's 51. Was it Puerto Rico? I thought it was Puerto Rico. Maybe I am. Oh. So they also have one that's like all of the United States. So they have like the full count. So that's something that happens a lot in health data sets that you download, and it's, why is this annoying? Well, because I can't get the sum of the death column and get the total deaths because it's literally double counted in this value. So what I would have to do if I really want to check, like, is this data set consistent internally? I would add this divided by 2, for example, compare it to this value, or pull out the number that's this United States value, pull that out, and then sum everything else, and then compare those two numbers to see if they're the same, right? Health data sets do this. Why do they do this? And it's because they typically expect people to open this up in Excel and not expect them to know how to sum columns or run functions on columns, so they add it as another row. And then that's problematic because that row is a calculated row. It's not raw data. So we go all the way back to the very first hour of part 1, day 1, and it's like, treat your data as raw data. Don't start adding things in that are unnecessary. So okay, that's something that I realized and learned from there. So we have all of these death counts. There is this thing called, if you see here, an age-adjusted death rate. So what is an adjusted rate? So first of all, it's a rate. So rates are always by time, right? So this is age-adjusted rate. The rate is in the year 2017, right? So that is, so it's not always per 100,000. That is just a convention because the proportion is so small. They report it in, like factors of 100,000. But if you like ask any epidemiologist, a rate is always like some count over time, right? So there, like, for example, there's no such thing as like 713 people, like, you know, what any of these, like 4,000 people just instantly died at that moment, like right now, right? Like if you remember calculus days, like the infinitely like instantaneous value, like that's not what's going on, right? And the rate is not 708 people just died right now. It's always over time. And so if you're looking at rates, always look for the unit of time, and it should be, that's how you can read the set of numbers. It's reported as per 100,000 cases, but it's the fact that it's a rate is always over time. So this is rates over across the year 2017. So that is the unit of time that's being calculated. So, so how do we calculate adjusted values, right? So the adjusted value, all you need to do to calculate an adjusted value is you take the numerator, which is the the count of the thing you're interested in. So we're looking at death rates. So that we're interested in counting deaths. So here, Alabama has 53,000 deaths. That's great. That is the thing that we're interested in counting. We take that number, divide it by what's known as the population at risk, right? So what is the population at risk as far as like whether or not you die? Well, it's the entire population. So you see this a lot with like that at risk thing is something that is very specific, and you have to make sure you calculate it properly because it is literally the denominator of your proportion. So if you put in too many people, then your adjusted rate is going to seem smaller than it is. And if you put too fewer people, like you're miscounting people, you're undercounting, then your adjusted rate is going to seem bigger than it actually is. So what is the population at risk, right? How do we define the population at risk of dying? Well, that's the entire population, at least in this case, right? So like if we think about like pregnancy rates, right? Now we have to filter the population count to like genetically female, right? Because like a man cannot get pregnant. So that denominator is really important. And then because it's going to be this number divided by like however many people there are in Alabama in 2017, it's going to be a really small fraction, right? So like let's say, you know, 250,000 people died in a state that has 1 million people, right? So that's like 0.25, and then you can see like these numbers can be like 0.001. So that's why you typically see these values multiplied by 100,000, just so the number looks bigger, and it's like out of 100,000 people. So this part is also another part that's really important when you're looking at the age-adjusted death rate. It's always over time, so you always have to find the time part. When it's reported as a number, find the per what portion of it. Because otherwise, if it's a decimal, then it's probably just the raw fraction. But if it's a whole number, then it's probably, you have to look for the per how many people bit. So in this particular data set, they reported age-adjusted death rates. So what is age-adjusted? I don't really know. You see a lot in data sets. Age is in different groups, right? So we have age-adjusted death rates for under 18, 18 to 25, 26 to 35, 36 to 45, etc., etc. So that means we need a death count for each age group, the number of people there is for each age group, to do age-adjusted death rates or age group adjusted death rates. I don't exactly know how they calculated age-adjusted death rate because it's just a single number. So I don't know how they calculated this number. I looked into the CDC website, went through a whole bunch of links, found some data set that's not a CSV, and just said, no way I'm dealing with this right now. So instead of looking at age-adjusted, we'll calculate something that's population-adjusted. One thing that's really important, especially when you look at a lot of these adjusted death rates, is that denominator that's calculating the total population, the total number of people, that has to come from what's known as a standard population. In the United States, we do this once every 10 years in the US Census. And so every 10 years, we get a count for the number of people, and then all of the researchers use that set of numbers as the standard population. What you'll also see is because we're in 2021 now, people are still using the previous census number, the standard population of 2010. So what ends up happening is a lot of these reports are always actually one census behind. So in 2017, they actually didn't really use the 2010, actually in this case they did use the 2010 census, but they also reported with the 2020 census data. Because this data set goes, if you looked at the original data set, it goes from 2017 and it goes all the way back to like 1999 or something. So the other thing you have to be very mindful of when you're doing adjusted rates is no matter what you're doing, they all have to use the same standard population. I cannot make a calculation with 2017 data on a 2010 census standard population and then compare it to census calculations in 2009 that was using the 2000 standard population. Those numbers maybe like, yeah, you can eyeball and get a sense of what's going on, but you are not allowed to make comparisons. They use a different standard population. They are not equal. So that's why people always use 20, until like very recently, like until last year, you still see a lot of people using the 2000 census data. And it's because they're looking at 2 decades worth of information and they want to be able to track what's going on. So that's another really important thing when you're looking at adjusted rates. Okay, so now we need to go and get census information, right? How do we go and do that? There's a library called Tidy Census, and just like Tidyverse, this will pull from the US Census and allows you to view census, download census data without having going to the website. If you've ever been to the American Community, like the ACS website, and tried to use that thing to download your files, if you've actually had to do that for a big study, like props to you if you had to do that manually, but there's a better way to doing that. The first thing you have to do, and don't worry if you don't have a Census API key, I have the data sets stored. But first you need to quote unquote install your key. The key is essentially like your username and password. So you don't want that stuff published on the internet, right? So yeah, the census website is an absolute disaster, and it totally, I'm not going to fix it. So we can get our API key. You'll get it in an email. The website looks super sketch, but it's welcome to the U.S. government, folks. So we can put in our Census API key, and the most important thing is to say install equals true, and then this is part of your code. This is something that you run, and you like delete it in the history so it like no one can see it, especially since I'm on like the internet right now. And then don't put it in your code, because if you email it to someone else, they have your API key. Like, so don't do that. So once you have it installed, you can then go and pull down census information. There's a function within Tidy Census called load variables, and we can say like, hey, I want the data from 2010. There are, let me show you the different ways you can use this. There's different types of like census data sets. If you know what these are, like, great. But they essentially have like, because the population is counted once every 10 years, we want to, what they end up doing is that like they project how the population changes between census counts. And so you can see ACS 1, 3, and 5, they have like 1 year, 3 year, 5 year projections. You can do that. So one of the comments I was getting was, yeah, the Census API, you can use this file known as renviron using the use this package. You can totally use that. I want to say when you run this function, it actually calls that for you under the hood and like just tacks it on in there for you. I would not be surprised if that's what it does. But yes, there is a file that has all of your passwords in it, and that's what's going on. But instead of you trying to do it manually, this function will install it for you without, mucking around your file system. All right, so we are going to pull, and I'm just saying like the ACS5. I guess if I'm pulling 2010 data, it doesn't matter too much. I used to work with census data a bunch. It's been many moons, so I don't remember that much about what's going on with the census, how like all of the other data sets are created. Because we're making a connection to the internet, we don't want to keep pinging the internet if we don't have to. That'll make the government happy, whoever's managing the server happy. So we'll say cache equals true. So if we run this bit of code multiple times, one, it'll be faster because it doesn't have to re-download it. All right, so what is this load variables bit doing? So all this is doing is looking at the 2010 ACS5 tables and literally giving you the variable name and what it's counting, right? So you can see, like, okay, if I want the total count of the population, like, it's also broken up by sex and age, but it only gives me total. And then it's like giving me just the male count, and then just the males under 5, and et cetera, et cetera. So each one of these is a totally separate data set, and it's broken up because we passed in, so it's broken up and into, we can say like the state level, the county level, whatever, but that's how it's broken up. And you can see if we want state population counts, we actually need like all of this data if we want to do something like splitting out on genders and stuff. So we need to first identify which is the data set that we want. So maybe I want to say I want all of the data that is, this is a little bit, but you can see like there is estimate total, like who lived in, like, do you own the house or not, and then your income, and then like a count. So it's counting a whole bunch of stuff. Why is the ACS website like a disaster? It's because you have to download these things one at a time. If you want like all of these income brackets, you have to go and download all of these files one at a time. And so we can actually use the computer to do that for us. So if you're kind of stuck and your ACS thing isn't working, there is an actual data set in the data folder right now called ACS 5 2010 vars. If you load that up, you get the same exact thing. So that's what I ended up doing right before we, just in case your API key wasn't emailed to you yet. So we have this whole data set of variables, right? And if we want actual population count, so I guess what I could have done is just getting the total data set. I didn't really think about that. But what I ended up seeing was like, hey, I actually want the breakdown by sex by age. So I want all of these data sets. And so this is just a good example of using functions in relation to API keys, because now that I think about it, the example is sort of moot without, you actually using the API and functions and loops and all of that. So we'll go through that bit of the example. So what I want is from here, I want to filter such that this concept value has the word age in it, right? So that's just one way I'm going to decide to filter this. So remember yesterday in the tidyverse, I believe we loaded it up. So in tidyverse, it loads up the string R library. There's a function called string detect. We can say in the concepts column, let me know if the phrase age is in there. And you can see like we have much fewer rows, right? We start off with 20,000. Now we end up with 6,000 different census tables. And then I can say like, oh, actually, what I really wanted to say was I wanted to filter such that the concept is really just sex by age. Because if we look at this, there's a whole bunch of other tables involved. So you can see like there's 49 tables in here. And so now that we know like, hey, these are all the tables that maybe we want to start looking for, now we want to use this identifier to download that data set. So how do we go and actually go to the census website and download this data set? There's a function within tidy census called getACS. ACS. And in here, we have to say, what is the frequency count level that you want, right? So let's go back to the question that we wanted to work on with age-adjusted counts, which is not that file. Oh yeah, it is this file. Age-adjusted counts, we want the thing by state. So that is the geography level we want. So we put in state. You can get things by county. Just so you know, zip code is not an actual thing. Zip code is for the U.S. Post Office, not an actual like census designated like breakdown. So okay, we have. I believe it's not a census designated breakdown. It shouldn't be, but yeah. So then there's another parameter called variables. The variable is, if we go back to like that filter data set, this is the variable. So let's say I want, you know, this one, males 20 years old. That's the count I want. I have to put that in the variables parameter, and then the year, I want this to be 2010. And so this will make a call to the actual census website. So I'll save this to a variable. And if I run this, it will go to the census website, download this exact data set, the 2010 data set, for age, whatever that age group was, 20-year-old males, right? So if I look at census data, I have 52 values, so it's District of Columbia, and instead of total, I think now this one actually says Puerto Rico. I really hope it does, or maybe like I bamboozled myself, and it's the United States. Oh no, there it is, Puerto Rico. So now it's giving us counts for Puerto Rico as well, right? And so this is the number of males who are age 20 by state. All right. So we have a way to download data from the internet. That's great. What do we need? So I need to like, of all of the data sets that we're collecting, so if I look at this data set, you'll notice that like, yeah, if I straight up download any one of these tables, there's no metadata in here that tells me what this thing is like. Actually, this variable is like a little bit of metadata, but it's not very useful, right? Like I'm gonna still have to go back to this original table and then be like, figure this out and then like join. But I really need like this label column to actually tell me in my data set what it's actually a calculation of, right? So I want this bit of information in my data set. So what is the next step I have to do here? Well, then I would actually have to say mutate, and I'll call this label is equal to like, this is males, like right there. So I'll paste that in there, and now I get a nice little count. So if I were to go through this process for B01001_008, and if I do it for 009 and 10 and 11 and 12 and et cetera, et cetera, et cetera, I want to be able to have that bit of metadata with me, right? So yes, we can do a left join. We can, but just so I can get this example across, all of the information we need. So what was the function that we needed to download this data set, right? This function here. We needed a variable. So that's this value called name. And then and then what is the metadata information in that final data set? Well, it's literally the column called value, right? So let's write a function that can take these two inputs and then give us the data set that we want. So what we can do is we can say download_census gets a function. So what is the two things we want? Well, so we want this variable, this thing called name, which is this variable. So let's call this var name. And then this other thing, which is the label. And let me spell this. The label. And then we can write our function, right? So what is the function? Well, the function is pretty much this thing that we just wrote. So a review to yesterday when we were talking about functions, you know, I introduced functions in all those separate steps because that's literally how I work. Write it for the single case, make sure your code works, and then try to apply it to multiple data sets. So we're gonna run that literally that bit of code, right? The only thing different is we pass in a variable name, and then that's it. We're not using this label right now, but remember this last bit down here, we took this census data and we mutated it to label. So we're gonna save that and then return our census data. So that's it, right? It's nice to know what your data looks like so you can think about writing like the code to make that calculation. Then once you have that block of code working, then go through the process of turning into a function, which I just did. Before I even go and apply this back to my data, like I want to make sure this thing works, right? So what is example inputs in here? I want to say, okay, this 0, whatever this value is, this table 4, and it's calculating males 5 to 9 years. So I'm going to pass in those two things, and then hopefully it gives me a data set, which it did, and it tacked on that information. Why? Because I literally told it to do so in my function. So that's great. All we need to do now is automate this process because there's no way I'm gonna copy paste this 52 times and get like any of this thing correct, right? But if we go back, we have that information, right? So remember yesterday when I showed you map, right? Pass in a column of data and it will understand how to work on it one item at a time. So we can actually do something very similar. So yesterday when I talked about the per library, in per, yesterday we used a function called map. There's another version of map called map2. So let's say yesterday in map we passed in 1 column of values. Map2 lets us populate 2 column of values. And then instead of map 3, map 4, map 5, if you need more column of values as inputs, you can use a function called pmap, and it all works very similarly. The question I got was, is the label returned in the data frame correct? Unless I copy-pasted wrong, I believe... Oh, it's not. Oh, it's not. Aha, so cool. So that was like a mistake, and it's because, again, I didn't use the actual label. So there we go. So that's why we check our work. That's why, give me 1 second. Download. Hopefully it is. Yeah, okay. So this label is now correct, right? And that's because I had that hard-coded bit here and I forgot to use that label bit. So again, that goes into yesterday where I talked about checking our functions. What I would definitely do now is I would probably end up writing a case and making sure that doesn't happen again. But yeah, with the live coding is hard. I literally have the notes in front of me and I'm still gonna miss certain bits of it. So that's the map function. So going into map. So how does map work? We pass in values and then the function. So what are the values that we want to pass in? So let us, this ACS variable that we created earlier, this, right? We want to pass in this name column. So I can say, this ACS, we want to pass in the name column. So you can use $sign to say like, just pull that column of values. We want to pass in that name column, and then we want to do the same thing and pass in the label column, right? So now I have just the names, and then in the same order, the corresponding label. And that's how our function works. Gives me a like the variable name and then a label. So now we then say, what is the function we want to use? The function is called download census, right? That's literally the function we named it. And then I'm going to call this, I'm going to save this to a variable. And what it's going to do is make this call 52 times, each one of those returning a data set. And then it's going to take a while. And I also realized that this code was a little wonky, but each one of those is going to make the same calculation and then return us that data set, right? So this is going to give us a weird object back. It's not really weird, but it's going to give us a list object back. So remember yesterday when I talked about map CHR for map character, we actually want this to give us back as a data frame object. So we don't get a list of data sets. We could just get one giant data set with everything that we need. So instead of using map2, we can say mapdf. The super shorthand answer is if you don't have the census data like downloaded, the API stuff working, you can download the raw data set with everything all in one go. Hopefully my computer didn't just like die on its on itself. So one question I got, what is the difference between mapdf, DFC, and DFR? I actually don't know. I don't think I've ever used them. And I can't really pull up the documentation other than right here. So as that's working, let me go and think about what's going on. Okay. So if we look at the documentation, there's right here it says like what is the difference between DFR, DFC, etc., etc. So it's whether or not like you tack on column wise or row wise. So I believe by default it's using mapdfc because you're tacking on the columns versus tacking on rows, or I might have flipped it, rows on columns. So yeah, I've never used it because I usually expect it to tack on that way, but I guess it's pretty common if you're downloading like a lot of time series data, like each unit of time ends up as a column, like years ends up as a separate column. So I guess you would use the other way to tack it on. It becomes not non-tidy, so that's probably a reason why I've never used it before. But yeah, so this is still downloading. I'm going to say I'm not going to run this again, but the cheater block of code is running this line, right? So we want, instead of a list of values, we want one giant data set back. And so that's what we're going to use. We're going to use mapdf, not just plain old map. All right, so I'm going to cheat a little bit. And if you got auto modded, I am very sorry. Hold on. Give me 1 second. All right. All right, cool. So apparently, like the percent greater than percent is like, depending on what chat system you're using, is not very happy with it. And clearly, I'm not going to run this block of code again. Let me see if I can stop this. And what we should end up with is the census data downloading all of the little bits together. So I'm going to cheat a little bit. I'm not gonna, I'll just sort of like paste in the little blocks of code. But we can then say like, hey, give us the distinct labels, and you can see like we now have all of that count data across all of our states, right? And if we look at census, you see that we have 2548 observations. So if we want to do like a visual check or another check, if we divide this by, I believe it's like 52, there's 49 tables, and that matches up, right? So we have the correct number of tables for 52 calculations, that's including DC and Puerto Rico. All right, so I was trying to see like, hey, I want to get gender breakdown. So like instead of like population adjusted, maybe we would try to get like age or gender adjusted breakdowns. Turns out that we don't have death counts for any of those. So like I sort of backtracked on that. But let me... mainly for time's sake, I am like copy and pasting. But we have our census data set, right? What I should have done is really pull out the total, but I was trying to get individual gender counts, right? So what I really wanted was give me the data set where it was just like the male under 5, like all the values that have values for male or values for female. How did I find that? Well, we can use string detect. We can use string detect just like before and look for these things, right? We're literally using this messy version of the data to help us find things. And then once we have this data set, well, how do I break up gender and age group? So then remember back in part 1 where we were doing that split, and I sort of referred to that yesterday as well. Well, there's this separate function. So we can separate on this little double exclamation mark, and we can say, well, make a column called estimate, make a column called total, make a column called gender, make a column called age group, and that's what I did. We separated into those 4 columns, splitting by the exclamation mark, and then estimate and total, like that's sort of repeated, so let's just get rid of those columns. And so now we end up with a nice little data set that is state, a variable, the count, and then that count is a gender count and an age group count. And this is essentially like a nice tidy data set for us, because now what can we do? Well, we can get total population by state. We can get total population by gender, by state, et cetera, et cetera. Like we can now answer like how many males there were in the United States, or how many males under 5 there were in 2010. So we can go do that. More importantly, we can then say the population state, right? So now, give me 1 second. Yeah, so now we can actually go do something like the census age. We can group by the state, which is name. So for each state, I want to group by the state. And then I can say summarize. The population is the sum of the estimate column. And so now I have 52 observations, so that makes sense. I have 52 state observations in this data set, and it's the sum of all the males, all the females across all of the age groups. So this is a way where we got all of the total population by state. And so now if we go back to our original question, I wanted population adjusted death rates by the state. Now we have the denominator to go along with the death count that we had before. So how do we do that? Well, that's a review from yesterday and the review from what I just did earlier. We can join those 2 tables together. What is the key that we want to join on? We're going to join on the state value. And so now we can say inner join. I want the top causes of death. then the population state data set, and then what are the variables we want to join on. So on the cause of death side, so this data set, we want to join on the column called state. So we can say state is equal to, and what is the column on this side? It's called name in all caps, name. And then I'm going to save this to cause of death state pop. Right? And so now I have a death count and a population count. Great. Now I can actually go and do population adjusted death rates. So how do I do that? Well, we can say mutate, because we're making a calculation on a column, and I'm going to call this death adjusted rate by population is going to be, how do we make this calculation? Well, it's going to be the count of the things we're interested in, which is the deaths column, divided by the population at risk, which we've called pop, times, by convention, it's 100,000. And now if we look at this, or if I make the, let's just look at the actual data set. If I look at this, now we have a death adjusted rate, and it's going to be different from the raw death count. Why does that matter? So let's look at this. California had almost 250,000 deaths, but its death adjusted rate is about 732. So let's compare that to a really small state like Alaska had 4,000 deaths, but it had a rate of 633. So it's not that far off from the death rate in California. So let's look at something that's a little higher. So California was around 700. Well, look at Wyoming. Its adjusted rate is 800. It's actually higher than California. And it's because the population is so much lower. And it's adjusting and accounting for that. And so that's how we can do this type of age-adjusted, or not, in general, that's how you do adjusted rates, right? Count the number of things that you're interested in. And most importantly, the most important part of this thing is, what is your denominator, right? So for us, the entire population is susceptible to dying for some reason. So that's how we find that out, right? That's the entire population is being susceptible is probably not the entire case. And I would almost take a guess initially when they were doing infection rates, they probably weren't counting children last year until recently, right? Because everyone was under the assumption that children could not get infected by COVID. So that's probably something that I would look into now that I'm thinking and talking out loud. But now if you're reading the news, what is that denominator, right? Because it will change how you can compare between two groups. And this also, again, remember, we're pulling this all off of the 2010 census, right? So just because the 2020 census came up, if values are using the 2020 census, you cannot use the numbers from that to compare it to the ones last year, because the 2020 census wasn't out yet. No one was using those numbers. And because that reference population was different, you cannot compare those groups. You have to redo the calculation so both sides are using the same population. All right, cool. So let us take a 5-minute break. And that is going to be the nice little intro review of stuff we did yesterday. And I guess the most important, the brand new thing, other than showing you what an adjusted rate looks like, is this little line of code here. After we install the API key, that's how a lot of data scientists download data. They go to the website, get a little key, and then they figure out how to pull data in automatically instead of going to the website and clicking through it one at a time. And then we can combine that with the per library, as long as our data set is already set up to contain the metadata that we want, we can download it all in one go. And that's generally the workflow I do. Before I query the website and whatever, I actually just go and create the data frame of all the inputs I need. One, I can visually inspect, like, is this everything I need? And then I literally make a map call or some other call to download all of the data set onto my computer. All right, so let us take a break. I'm going to say let's come back at 15 past the hour. And if you have any questions, let me know. Okay, cool. All right. So next thing, let us hopefully in about 30 minutes, the website will be updated and I can give you a link for it. So the next thing we're going to cover is on, what did I want to cover? survival models. So we're going to create a new file, and I'm going to save this file. And just so I get the numbering correct, so we talked about 0, 2, so I'm going to call this survival. And so what I'm going to say for survival analysis is I haven't fit one of these models in a really long time. Graduate school has sort of taken other priorities. To everyone else, if you are trying to get if you're trying to start off with survival analysis, and I will say, like, I am going to give you the introductory intro to this introductory intro that hopefully will help you move to use, like, or learn about other more in depth on how to use survival analysis. So this is a tutorial that was created by Emily Zaber. She now works at, ooh, I forgot where she works. She used to be in New York City, but it's one of those like large hospital systems in the United States. I believe that's where she works now. But anyway, she put together this tutorial for survival analysis, and we'll essentially go through a little bit about what is survival analysis and how you can go fitting a survival model, what your data needs to look like before you go and fit a survival model, and how you can sort of interpret some kind of data set for that. So what is survival analysis? Survival analysis is the type of analysis you do when you have censored data. What is censored data? Censoring essentially means that you don't know what happened to this person. Like, you just don't know what happened to this person, right? So a lot of times when we're looking at our data set, we care about some event. Oops. There is way too many things going on. Sorry. There we go. Thank you. So censored data. So there's Emily Zaber's post. So what is censored data? It happens when we don't know what happens to the person. So when we are typically thinking about our data analysis, for example, there's 2 treatment groups for lung cancer, right? And we want to know if one treatment is better than the other. And by better, we mean like increases their survival rate, which is another way of saying like this person dies later or like stays alive longer. Censoring happens when, let's say, for example, like this patient is coming into your clinic and they just stop showing up, right? So the fact that they stop showing up to your clinic or for treatment, you don't know for sure whether or not they stopped showing up because they died, or did they just stop showing up because they moved to out of state because medical expenses and other like life factors they just didn't tell you and they stopped showing up, right? So there's no way to know whether or not this person stopped showing up because they're dead, or another way, or a less grim way of saying it is like they didn't, they stopped showing up, or like they met the event of interest, or you just don't know and you lost them to follow up. So that is the whole point of using survival analysis, is sort of like using all of the data you have, because otherwise you would have to filter your data where you all know definitively, like, did this person die, yes or no, right? So it's a way to sort of use all of the bits of data that you have collected. All right, so let's work on a survival analysis example. We are going to load up tidyverse. All right. We're going to load up a data set called cancer. I'm gonna name it cancer. This actually comes from lung cancer data from the Python world. I just picked this one because the documentation for it was a little bit easier to read. But this is lung cancer data that comes from, let me actually post the link of where this comes from. So this comes from a scikit survival lung cancer. I believe it's also like on the intro page. So this is a data set I pulled from out of scikit survival. You can see it's like literally the same figure. Like, did you lose them because they just stopped showing up, they dropped out of the study, or something like the event actually happened? So this is data that is coming from the Veterans Administration lung cancer trial. It consists of 137 patients and 8 variables, and these are all of the variables that they have. Main thing of interest is they were either on standard treatment or test treatment. Typically, there's one of the arms is typically not like no treatment for a lot of these things, because if there's already like a standard of care for in like for a medical treatment, like you have to give it to them for ethical and legal reasons. You can't give them less than that. So not every single study is going to be like a placebo study. And then they're saying that like if they get lung cancer, does the type of cell in the lung that has become carcinogenic, does that matter? There's other scores being involved, other demographics, and then most important, whether or not the person was dead or alive in this particular study, and then how many days was that person quote unquote alive, but it doesn't have to be till alive. It's quote unquote until you either lost them to follow up, they met the criteria of interest, so they died, or they dropped out of the study. So it's the amount of time there. So let's see what this looks like in our data set. If we look at the cancer data set, we see status, like whether or not they're alive or dead, their survival in days. So like this is, for example, someone that was lost to follow up, their age, their cell type, whether or not they have prior therapy, and then their treatment arm. So this person was on standard treatment. And so this survival in days is really important. And if you go back to like the very first thing I showed you when we were doing table joins, and using that percent dash dash percent to calculate the difference between two times, and then dividing it by year or dividing it by day, we use that calculation to create survival in days. And you know, maybe I can expand on that part. So we do a little data cleaning for that for like future iterations of this class. But you need to get your data set in this format, right? And so essentially you would need to start off with 2 columns, like time they entered the study, time they left the study for whatever reason, right? And then you can make that calculation there. So that's the cancer data set. So what is survival analysis? So typically when we are looking at survival, or when we are doing survival analysis, we are looking at what's known as a Kaplan-Meier curve, right? So it's that little curve, it's that little plot, if you've ever seen it before. It looks like this, right? And the way we read this curve is on the x-axis is amount of time, right, since treatment or since whatever, so the amount of time. And then on the y-axis, it's the probability of survival, right? And so when you're conducting studies or when you're coming up with new new markers to like early on for early detection, you have to, a lot of people will present like, hey, early detection increases survival. Not always the case, right? Because now you have to think about, there is a bias involved with a lot of these things, and you have to make sure that just because you detect the cancer earlier by definition, they're gonna live longer because you started them like further in the past, right? And if you don't do anything about it, well, their actual survival rate didn't really change. All you did was just, give them a quote unquote extra 3 months because you found it earlier 3 months ago, but you didn't intervene or do anything. So when you are doing the analysis for all of these like medications, or especially like things that are trying to do early onset like identification, you have to be very mindful. Like, hey, is doing this actually helping the patient? And then if it is or if it isn't, like is it ethical or correct to like present survival analysis data, because that's just a bias in your data collection. So this is what's known as a Kaplan-Meier curve. It's on those two axes, time on the x, probability or survival on the y. So how do we go and do this in R? So in R, there is a library called survival. And what the survival library does is it helps you do survival analysis. So how does this function work? It's a little bit different from the rest of tidyverse and everything. The little coding pattern is a little bit different, but that's sort of just the nature of how this works. After survival analysis, we'll go into the logistic regression example with tidy models, and I'll just hint that tidy models has a way to do survival analysis, so a lot of this can translate over into something that's much more consistent. I just haven't, I don't have the code for it, and I'm going to treat this with this is an introductory class, and I can get away with it by just showing you the basics and how things are connected to one another. Okay, cool. So we have the survival package. How do we use it? In survival, there is a function called serve for creating a survival object. What are the two most important things in survival analysis? We need to know their status and then the day until event, right? So essentially, like, how long have they been alive for? And that doesn't mean that they died. It can also mean you lost them to follow up. So we have our cancer data set. The first thing we pass into survival is the survival in days. So whatever name you name that column, we pass in that. So this is, of all of our people, these are the days. And then we pass in the status. And you'll notice that we get this set of the only thing that's different between this outcome and the regular days column is if you see a plus, it says that this person was censored, right? So we don't definitively know this person died on day 123. We just know they stopped showing up, or that person is right censored. And so if we that's what this prints out as. This is actually a more complicated thing under the hood. But what we can do is we want to go and actually create that Kaplan-Meier curve. How do we go create that Kaplan-Meier curve? There is a function within survival called serve_fit. What we end up doing is we take this entire survival object, we paste it in. That's why this syntax gets a little bit wonky. We're not putting in any other treatment variables. So like if you've ever fit like a model before where like you're just drawing like I'm trying to like figure out like a good way to explain it. We need to pass in like other variables that we're going to use to treat this survival curve. But if you're not using any other variables, you can say tilde1, just saying like, hey, it's like the identity essentially. So that's how you specify like I only care about looking at probability of survival over time. Then we pass in the data set that we care about, and we get this survival fit object, right? And it says that there's 137 events, the median survival rate with whatever across all time. that's all nice, but we actually want to look at this in the plot. So we'll save this to a variable called sf1. So we have this survival fit, right? So in here, it's done all of the calculation it needs to draw that Kaplan-Meier curve, right? So if we look at the contents in here, and that's why like this part, it's like a weird thing in R, and tidy models is one way to make this like a less weird. But in this survival object, the two important things we care about is the time column and then the percent of the survival probability. So how do we go and plot this figure or plot this survival curve? You can use, I think you can use the built-in plot function. I think this works. Yeah, so you can literally say plot SF1. It's kind of like here it is if you need something super, super quick. But there's another library because we like ggplot. There's a library called servminer. And in servminer, there's a function called ggsurvivalplot, right? So, and all we do is we put in that survival fit object, and it gives us our survival Kaplan-Meier curve. And so we get the same results as, actually we should do this. Do we get the same results as the Python data set? I really hope we do, right? So one of the things here to note that it's also plotting the confidence interval. So we can do all of that. There's many different ways we can tweak this figure. But the other thing that we can do with this is, let's say we care about, so on the x-axis, it's number of days in this case, right? So it's the survival probability across time, and time is measured in days. So let's say we want to figure out, given this survival object, what is the probability that this person survives 1 year from, like 1 year out, right? So 1 year is 365.25 days. So we can now get the probability of survival is 9% with that confidence interval. How do we look this up on the graph? Well, we will look up around 365 is going to be here. We look up and across, and that's roughly the probability of survival there. Right? So that's how you read a Kaplan-Meier curve, and that's how you create a Kaplan-Meier curve, and that all comes back into like, look at the input data set that this came in. We need a status, and then we need survival in days. Right? And it tells us whether or not this person is censored or not just by knowing like comparing between status and the survival time. That's how it can tell whether or not this person is censored or met the event or something. Okay, so let's do more things with this. And one of the question was like, you would be able to add a vertical line marker. Yeah, you totally can add a vertical line marker. And then again, I am going to point everything to Emily's post. And somewhere in here, yeah, so wait, actually, I think she drew that manually. But yeah, you can draw the vertical markers. You can make calculations. In ggsurvplot, you can actually do plot this, what did this call this? A risk table. So let me show you that. So we can literally say risk table is true, and it will give us a little risk table at the bottom. Yeah, if I make this big enough. So it says like, hey, at 250 people, we started off with 137. The number of people at risk is 18. So you can get like a sense of the risk or probability from that, looking at that as well, right? And so this goes back into the thing I just talked about with census data, which is your population that is susceptible that really matters, right? Because that defines literally the denominator. And that's the thing with using survival analysis versus just looking at raw proportions, because you're going to have a bias just looking at raw proportions. And I will literally just point to Emily's paper, Emily's tutorial on like, she does the raw calculation, compares it to survival analysis, and then you see like there's a discrepancy and the survival and why you use survival analysis for this type of analysis. Okay, so I showed you about survival analysis, this Kaplan-Meier curve. We can actually use the same curve, so I'm going to save this. I'm going to call this survival 2. And so let's say we want to use a different variable, right? So one thing we care about is probably the variable called treatment, right? Like how did the survival change across the two different types of treatment? So the code is going to be exactly the same, right? So a lot of the weird thing and the funny thing about like doing all of this like modeling stuff is like the code that does the model is like, that's it. Everything else is like, now I have to deal with it, right? So a lot of people who are like, oh, I want to learn how to do like this really cool machine learning technique, and it's like, yeah, really, like the code bit is like 1 or 2 lines typically, and then everything else is like thinking about the problem and then double checking, or you manually running calculations to make sure what your assumptions are is correct. All right, so we have this model that is just on treatment. So we can do the same exact thing as before, right? So I can say like GG survive plot, put in this survival object, data is cancer, by default, the confidence interval will show. And then so now if I look at this, or the confidence interval will not be shown, but now I can look at the survival curves for treatment, which is in red, and for the standard, which is in red, and the treatment, which is in blue. And in general, you want the thing that is like higher up or like closer to the top right corner. It means that like that person is surviving longer. But the other thing you want to know about survival analysis is like, if I at time equals infinity, everyone's going to die, right? And so one thing you want to be very mindful of too when you look at survival analysis, like let's say I literally took a flip of this of the test group, and it's going to be like, hey, the probability of survival for like 200 days is super high, but by 300 or by a year, like the survival probability is all the same, right? So that's also another signal that like, is this treatment really like a better treatment? Like, yeah, like the chance of you surviving to a year is higher, but you're still, the survival rate at a year out still hasn't changed, right? So that's one thing. One thing you have to be very mindful of when you are doing this type of analysis is like, just because one line is higher than the other. So like even over here at time equals 500, and let's use like, yeah, I don't know how many years that is. Like 500 divided by 365, this glorified calculator known as R. So a year and a third out, right? So I don't even know what a third, that's 4 months. So 1 year and 4 months out, is this probability really that much higher than the original treatment? So I'm going to slowly say that like this treatment probably didn't work, right? Even though that like over here you see it being a little bit higher, it's not really that much higher. And so what we can also do with Kaplan-Meier curves is add more variables. So in part 1, I showed you about logistic regression, how we can add models, add variables to logistic regression, et cetera, et cetera, et cetera. So we can literally say like, how does prior therapy affect this model? So I'm going to call this like model 3, and then let's look at this. How does adding more models change your Kaplan-Meier curve? So first, it does the what is it called? Like a cross product. Like every unique combination it will draw a separate Kaplan-Meier curve. So we have ones that is standard treatment, no prior therapy, standard treatment with prior therapy, test treatment, no prior therapy, test treatment, yes prior therapy, and the test treatment prior therapy is in purple. So at first glance, it does seem that like if I look at purple and this greenish one, maybe this is a study or a medication that is like, this is a test treatment for patients who have tried other therapies before and didn't work. Maybe you can make a case around that, right? Because this purple line seems to be higher. If you look at like a year out, it is higher than the original thing. But then all around statistics is like, yeah, just because the line is higher, is it like statistically significantly higher, et cetera, et cetera. And that's the question that we want to ask ourselves. The way we can do that, or like, how do we add in more variables, right? So like maybe age plays a factor, and maybe other reasons plays a factor. That's all data that we've collected, and especially if you're in a hospital, that's data you're going to have. What other demographics or other medical conditions like affect the treatment outcome or the probability of survival? Yes, I guess in theory you can just keep adding things here, but you can see like the number of lines will explode. Like the second I try to add a third variable in here, like this figure just becomes unreadable. So we need a better way, right? And so one way to look at how these variables relate to one another in a survival model is using a Cox proportional hazard model. So that's like the statistical test to like sort of look at survival data. So how do we go and fit that model? So there is a function called Cox proportional hazard. That is the name of the statistical test. That is the name of the function that we're going to call. And this part looks very similar to fitting the survival model right down here. So I can literally copy that survival object. So we're looking at survival in days, the status, and we're using the treatment and therapy variables. And then that's it. That's, again, how you fit the model, right? I'm sort of from copy and pasting because I specified the data here. I technically don't need to know. It knows like this is all in one data set. All right, so that's it, right? Like, again, fitting the model super easy. Explaining the model is like infinitely difficult. So how do we read the values in here? So let's call this Cox, or I'm trying to like make sure I don't call this like a word that makes like a lot of sense that's being used by other stuff. So here, like, okay, the thing that like people get like really like in trouble for is staring at p-values. But you can see like actually like this really doesn't seem like a therapy that works, is like my initial guess. And again, like I've already proven that to myself by looking at the figure, but if you want like the statistical test to like tell you like, hey, this doesn't seem to be working. But just like in logistic regression, how do we interpret these numbers? The way we interpret these numbers is we exponentiate the coefficients, and then reinterpret them as what's known as a hazard ratio. So in logistic regression, we interpret our coefficients after we exponentiate them. They're interpreted as odds ratios. In Cox proportional hazard models, the last phrase, the last word in that model hints at what is it a model that's telling you. It's about a hazard ratio. So how do we get this information out? So a bit of review to part 1 again. In the Broom package, we can take any model object. So that's this Cox model object. In Broom, there's this function called tidy, right? And it gives us the table that's just the coefficients table, right? We still need all of this other stuff, like to make sure like this, like to inspect the model and to make sure that this is a quote unquote good model. But we're also we also have a lot of interest in just the coefficient table. Why is this also useful is, well, if you're doing your stats in R, this is a table you can write to a CSV and then just hand off and have someone else deal with it, right? Or you just need to save it as like results, or maybe you're trying to put it into a paper, et cetera, although you wouldn't really report it like this in a paper. But you can save out these data sets as data sets for other people, right? So we talked about pipelines and all of that stuff. So how do we go and exponentiate? There's a function called mutate. We can calculate the hazard ratio by taking the exponentiating the estimate column. And so here it is. That is our hazard ratio. How do we go about interpreting this? So remember in logistic regression, it's like for every 1 unit increase in this, the odds of this happening increased by this many times. Well, that's pretty similar to how we interpret hazard ratios. So for every 1 unit increase, and in this case, what is a 1 unit increase of treatment? It means from going from standard to test. So from being in the study or being on this drug, the hazard like increased about 1 time. And in math, like multiplying anything by 1 is just itself. So it's saying that like, hey, like this test didn't really do anything. Like the treatment didn't do anything or didn't do much, right? And so the other thing with hazard ratios, and it's very similar to the odds ratios in logistic regression, is it's bound from 0 to infinity. So the amount of quote unquote space between 0 and 1 is the same from 1 to infinity in this interpretation. What is that? How does that affect your interpretation of these results? Typically, things greater than 1 is like in a hazard ratio form, is like this is what's causing things to be worse, like increasing your hazard or decreasing your chances of survival. And things that are less than 1 are lowering your hazard or increasing your probability of survival. So you can see here, it's because the therapy, having prior therapy, seems to be quote unquote protective. It's not really like a clinically significant result, right? So it's all hovering very close to 1. So it's not very protective. But you'll see things that are like 0.4 or like 0.2 or like 22. Those are going to be things that like jump out at you. All right, cool. I know the website thing is sort of like, I think it's fixed. I can probably get a link for something. So let's take another 5-minute break. We'll come back at like 55 past the hour. And so if you have any questions around things, do let me know. hello.
So sorry, go ahead. After the break, I'll talk to you.
Oh, yeah, you can ask the question.
Yeah,
Y-
basically, I have a confusion. This is second time I'm coming on to this thing. So how often do you take this course?
Oh, how? So the question is how often? Sorry, I'm repeating the question because there's multiple streams going on. So the question is like, how often do I teach this course? So this course is part of my dissertation research,
Okay.
and so it is. This is going to be the last, I guess, live session for until like I graduate in like the next couple of months. So it's a big part of it is around. So a little bit more about like the actual dissertation project. It is data science for the biomedical sciences.
Mm-hmm.
So it is trying to teach like data science concepts, but like completely in this realm of like medicine or like medically like relevant things. And so the part of the dissertation is like how do we like introduce all of these data science concepts using like one more realistic data, and then two like teaching it with and like usually stuff like survival analysis, and then like stuff like running calculating like rates and all of that, like that's not something you're typically going to see in a traditional data science class. And so it's mainly trying to create like a set of materials that is domain specific, and then in the academic portion of it is identifying how data science education differs from traditional computer science education.
Uh,
And
yes, yes. I mean, I basically work on oncology side, and I do see several analysis in a day and day out. So yes, you are right. I mean, this is so much helpful. I mean, has this session been recorded too, as like others?
yes, so this is all going to be recorded. Hopefully you've been getting my emails. So as long as you've been getting my emails, like give me until this weekend, and everything should be on YouTube, and all of the code that I'll have will be posted. Someone asked me between yesterday and today, because I keep referring to part one. I will also put the recording and the stuff I did for part one, because a lot of it is built on top of that, even though the individual code bits itself isn't built on top of it. The
Concepts.
the concepts are. And so I'll give me like a couple of days, and a lot of that email will all be linked in there. So it'll just be a big giant email with links.
Good, good, good. Yes, that was my second part of my question. You answered that. And the only other thing is you had what you call R and the how you do the same thing in Python, right? So you had the first part is was the first thing was in R and second thing was in Python. So I was trying to find out the GitHub page for the same programs that you did in R and Python. So
Ah,
I just
yeah.
wanted to check.
So the question is like, yeah, this is supposed to be a book that's written in both R and Python. Um, so in the earlier parts of this book, you'll see like it's color coded. The thing that's in blue is going to be, this is the R related bits, and if you scroll right under, this is the Python translation.
Okay.
So when I'm done with this project, everything that's being covered, so even the stuff down here, it gets a little weird when I get into really specific machine learning things. So that might be like separate chapters. But stuff like survival analysis is common enough that it's going to be set up in such a way where there is, here's the R code for it, and here's the Python code for it. Even a lot of the machine learning stuff, like I'm trying my best to write it in such a way where it's language agnostic, and then literally just putting in the code that is just, here's the code for the thing that I just tried to describe. So that was another big academic exercise for this project as well, which was how do all of these data science languages differ from one another? And, like translating between R and Python code, you really appreciate some of the things they've that the people at our studio have done. And then I also appreciate some of the things that people in the Python community have done. And so like there, you can see like the different like architectures and decisions being made. But at the end of the day, like once you understand the concept, like the code bit is really like, especially when you're fitting models, like literally the code bit is like one line of code, right? So it's like, how do you do like all of this calling functions and working with your data set? That's actually the most important thing.
Definitely. I mean, I agree with you on that. Mine was basically I use SAS day in, day out. So we use SAS model, I mean, proc life test and all that stuff. So my intention was to write something like whatever you did. I greatly got inspired by your work. Great kudos. Hopefully, if I can send you any kind of thing, I'm willing to do it. But I so love it that I want to do something very similar to what you did for SAS and R. You know how you can do it in SAS and R. But as my team is progressing from SAS based to R now, so it's a huge, big company, pharmaceutical company, and they are moving from SAS to R, and that's when I'm trying to fill in that gap.
Yeah, I know there's already like a Springer book that's like SAS or R for SAS users or something like that.
Yes,
I've
he has it. He has it, but what it is it's little kind of outdated because the most of the libraries that we have did not have it. The other thing is, uh, it is not dynamic. As it is, it's something like like you can't see and compare the same test results. Like say when you run the proc means and also the mean, right? You see the actual difference, then people could appreciate much better.
yeah. And then so hopefully this also, because this is very biomedically focused, yeah, I hope that it becomes like a reference. Like if you take what I'm trying to do and you replicate it in SAS, hopefully, yeah, it becomes like a good reference point for
Yes,
how to
yes.
translate between things. I I've only used SAS very like only for a little bit for like 2 years, and like yeah, I never even got to the point where I was writing SAS macros, which is the equivalent of functions, because a lot of the data sets when we were getting in from the CDC were essentially like SAS data sets, and so we
Hmm.
didn't have to process them as much. Like the proc data steps were usually just recoding that values, and then it was just okay, now just do proc logistic, and then that was it. So yeah, my SAS knowledge is very limited, but yeah, I the other big challenge with putting together the set of materials was like one, finding the teaching examples. Like the data sets in here are I tried my best to make them so like I don't get in trouble for publishing them.
No, you,
And the
yeah.
health data sets are really useful. I think the fact that the Cynthia project from MITRE gave you like a mock hospital database system is probably like my saving grace for making this project work. And so yeah, if even if anything, use this as a collection of data sets, and it's I just hope that I don't have to see like iris data or like Titanic data anymore. If it's supposed to be for a medical context, let's actually like try to find something and use medical data for. Um,
This is something like try maybe whenever you have time, look at the clinical FD. This is something that I put up, which is having the tidy data, or in the medical world we call it as SDTM data, and also they have Adam standard data, which is available from online. It's freely available. They have a mock study, and you can it's that medical data, right? You have that everything where the variables have been standardized and you can use them all together.
oh, cool.
Yeah, the
Um,
clinical FD, but you can take a look later on, and we can offline, maybe I can send you an email, or we can talk later about that.
all right, uh, I will bookmark clinical FD, and then I'll start the. Ooh, um, rest of the next part of class. So the next part of class, so we talked about survival models. As far as like coming from my own experience, doing my master's in public health, most of the stuff that we were essentially taught and like these are fundamental things was around like logistic regression and survival models and stuff like that. And so that's sort of the um, motivation and why the examples are the way they are. So the next thing I'm going to talk about is quote unquote like the more machine learning side of things. Like I know like people define things very separately, like very differently. This is how I am going to define machine learning. I am going to define machine learning that is one, your main goal is not to create inferential models like how like describing how why one variable relates to the outcome. I am going to define machine learning models as my main purpose is to create a model that is predictive of new data points, right? That is a different objective. Like I'm not trying to explain, how much or why prior therapies is how that affects your survival, right? I'm just trying to say, like, given this patient and all of these inputs from the hospital data, is this person gonna live, right? Or, you see this a lot in a lot of medical imaging cases where it's like, here's a picture of the eye. Does this person have glaucoma, right? I don't care what the reason is. I just need to pick the machine to tell me, does this person have glaucoma, right? And so you get into a lot of trouble because a lot of these machine learning methods, they are not as interpretable, and that's why you hear people call them like black boxes, et cetera, et cetera. The workflow around machine learning models is also a little bit different because it's focused around predictive models, right? So another big, when we first did logistic regression, I fit the whole model on our entire data set because it was a self-contained study. And then I can say like, hey, this variable relates to the outcome by this much, right? In machine learning world, and the way I'm describing it is, I'm not trying to say this variable relates to this outcome by this much. I'm just trying to say like, here's a model. If I have a brand new patient come into the clinic, what is their chances of whatever? So that's why originally in the set of materials I put logistic regression in like the first part, but I didn't talk about predictive models. It was just, here's a model, here's how you interpret the results. In a lot of epidemiological and medical studies, that's what they do. They collect the data, they analyze the results. They're not trying to say, this is the model that we implemented in our hospital for an alert system. That is very different. And the modeling process is different if that is your objective. Okay, so with that out of the way, we are going to create another file called, I will call this, what did I call this? ML for machine learning. So before we even go through machine learning, let us go back and review logistic regression. A lot of these concepts are going to be repeated. So how do we fit, so let's load up, so actually before we even do that, let us restart the R session so all of my data is all clean, all of the files are all clean, I don't have to worry about random things. I'll post this one more time. The temporary link to the website is up, so you can go to it. It's not populated or anything, but at least you have code to follow along and scroll through if you're not coding along. At least you can follow along a little bit easier. And then at least this is the reference that will exist when the site goes offline, when I actually go update it. So I will try not to update the website until very late tonight. All right, logistic regression. Let's load up our data set. We're going to use the medical data library. This is a library in R. We've seen this when we worked with logistic regression in part 1. It comes with a data set called blood storage. What is the blood storage data set? So this is a retrospective cohort study of the effects of blood storage on prostate cancer. So essentially, we already know from the title of the study what are the two variables of interest, right? Prostate cancer. I just know they're trying to see if there is a recurrence of prostate cancer, and one of the variables of interest is how long the blood was stored, um, like in storage during a procedure, during a transfusion. So that is roughly the context of this data set. So there's going to be a column in here called recurrence. It's going to be a series of zeros and ones. So it's a binary variable. If it's a binary variable of zeros and ones, the most common, and probably if you are going to fit any model, fit a logistic regression model, right? I'm not going to go into detail the math behind logistic regression like I did during part one, but this is sort of a review. The other variable of interest, and there is one called RBC age group. So this is a variable that denotes like how old that blood for the transfusion was used, and it has 3 different categories, and it's encoded as numbers, but there are 3 categories. And then we have other things about like the volume of the prostate, the size of the tumor in grades. We have other biochemical markers as well. So that's this particular blood storage data set. I am going to, and this blood storage data set comes with the fact that we loaded up medical data. It's just part of this is a R package that literally has medical data in it. It's maintained by Peter Higgins, who is a gastroenterologist at the University of Michigan, and he also teaches stuff in the R world. And so for those of you also listening, there's also a conference called R/Medicine. And so those are the people who work in medicine who also work in R. That is a little bit different from the R Pharma conference and group of people. Those are people who work in pharmaceuticals, and those are more clinical trials type of work. Max Kuhn, who's the author of Tidy Models, he runs another conference. He used to work for Pfizer. He works for RStudio now. He sort of chairs, or he's like involved with a conference called the like non-clinical stats conference, and so that's the pharma people who don't do clinical trials. So there's those 3 different types of groups in the R world that work with medicine and medical data. Okay, first things first. Our blood data set, if I look at for example, recurrence, it's a sequence of zeros and ones, right? I want this, because it's logistic regression, yes, it's 0 and 1, and it can do the math properly, but I actually want this to be a factor variable. And factors in R, factors is what R calls a categorical, like a category, right? They can either be ordered or not, but they're just categories. So they can be discrete or ordinal. It doesn't matter, but it's what R calls a category. So I want to take the variable of interest and turn it into a factor variable. This is one way of doing it. The other way of doing it, the more tidyverse way, so you might see this in base R. In tidyverse, what have we've seen code written this way. We take blood, we pipe it into mutate, and then we say the column is equal to as dot factor of the column, right? So that's the tidyverse way. This is the old quote unquote base R way. It's not really old, but you'll see as you get into more and more like outside of like introductory R world, like you'll see code written in different styles. All right, so the other group that I care about is there's a variable called rbc.age.group. And so I'm going to recode this as a factor variable just so we can get through the logistic regression examples a little bit faster. So let's review a little bit about logistic regression. How do we go and fit this particular model? So we can create a model object, and the function we use is GLM. And then in GLM, we provide the formula syntax. So we put in our outcome variable or our response variable or your y's or your dependent variable, whatever you want to call it, depending on your field. That goes on the left-hand side of this tilde symbol. And then all of your x's, predictors, independent variables, all of that goes onto the right-hand side of the tilde. And then in here, we put in the variables that we want to look at. So we care about our RBC age group. That's going to be the variable that it is. Because it's already a categorical variable, R and a lot of these R functions automatically does the dummy encoding for us. So like because we just had this conversation around SAS, not every single proc step in SAS does the dummy variable encoding, but it pretty much will happen automatically for you within R. And then tidy models, which we'll talk about in a little bit, definitely makes it all standardized that way. Then we pass in our blood data set. And because we are using the generalized linear model, there are other types of linear models, not just logistic and draw a straight line. We have to tell it to do logistic regression. And the way we do that is we pass in family equals binomial, and then it will perform logistic regression. For the statisticians out there, you typically run summary of this model object, and you get traditional statistics output. And you can see here that it automatically dummy encoded our variables. So we have 3 values for RBC age group. It dropped one of them. That one is the reference value. And then we have the coefficients for the other groups in that category. So right before when we talked about survival analysis, I talked about like, hey, most of the time we need this other information to make sure our statistics is correct and we want to inspect the model, etc. But at the end of the day, we really only care about this coefficients table. So given the model, we can pipe it into, so remember there's the Broom library. It has the tidy function, and it literally pulls out the table for us. So again, this is great because now you have a regular data frame. You can save it out to a CSV. You know, maybe if you're doing a, like for me, when I'm going to be running this code through Python and R and whatever, I want all of these tables as CSV files so I can compare the values, right? So now I have something I can save out. Because we're doing logistic regression, just like with survival analysis, we have to interpret. So in logistic regression, this notation is known as a log odds. So that's why if we undo the log bit by saying, by exponentiating it, we get what's left of that term, which is the odds. So this is the odds ratio. And so now we can see like for every 1 unit increase, so what is a 1 unit increase here? It's going from RBC age group 1 to RBC age group 2. That is the 1 unit increase. The odds of having cancer reoccurrence increases by 0.9 times, or essentially it decreases, right? So because it's multiplying by a value under 1. So for the other value, for every 1 unit increase, well, you're not going from 2 to 3, it's going from the reference value. So it's going from 1 to 3. That is the interpretation of the 1 unit increase portion when you're working with logistic regression. It's always in relationship to the group or that category that did not show up in your tables, right? So you can see like the RBC age group, these odds ratios are pretty small, like pretty similar to one another. Yes, I can also look at the p-values and see it's a non-significant value. So it does, it doesn't seem like age of the blood being used for transfusion is contributing that much to the odds of having a cancer reoccurrence. And by cancer, I mean for prostate cancer. So these are also all males, right? So for now, if we were thinking about everything else I talked about with like people at risk, it makes no sense to have all of your patients in your hospital. The people at risk of prostate cancer are people who have a prostate. And so you can define that however you need to. All right, so that's really all it takes to fit a logistic regression model, right? So like this bit of code, um, you can essentially copy and paste. And how do I add more variables to a model? Well, I literally use the plus symbol. And if I have other factors, I can put it in as that factor, right? And so that's how you do adding more variables in R. There are ways, literally in this notation, you can make interaction terms, et cetera, et cetera. I believe it's literally using the star. So like, if I had done age star p-val, it'll give me the interaction term there. So this is all around what's known as a formula method in R. So you can look more into that, but we're not going to talk about interaction method. That ends up being more in inference world. That's how I see it. So we're not going to talk about that. But that's it. So again, making the model pretty simple, adding more variables to the model. You're literally using the plus symbol for add. All right, cool. So when I talked about logistic regression originally, we didn't talk about inference or predictions, right? You can technically predict on this, but let's see how this translates into another programming like style. It's not really a style, but there's another library called Tidy Models written by Max Kuhn. And what he has done is essentially, if you've heard of scikit-learn in Python, scikit-learn or Python got super popular for machine learning stuff because pretty much every single machine learning model you needed was in this one place, right? And that originally didn't exist in R. So Max Kuhn wrote a package called Caret, tried to condense all of the different ways you can do statistics all into one package. It was originally called Caret. The successor of Caret is called Tidy Models. All right, so how do we use Tidy Models? Well, there's a library called Tidy Models. So we're going to load this up. It's going to take a while to load up, but it has a lot of stuff in it. For everyone who's hanging out, Max Kuhn and Julia Silge are currently working on a book called Tidy Modeling with R. It is their book for working in tidy models. They're pretty much done up until like the last bits of the book, but so all the intro stuff, I highly recommend you read it if you want to figure out how to use this library. So please take a look at the Tidy Modeling with R book. And I talked about this in part one, but there's literally the R4DS Slack community. There is currently right now a book club that's reading through it. There's multiple times, so if you want to read through, and typically people meet once a week or once every other week to talk about the chapters as they go through tidy modeling in R, that book. All right, so tidy models. How do we take this logistic regression model that we just made and how do we write it in regular tidy model syntax? So all we do is in tidy models, there's a function called logistic reg. And guess what that does? And gives you a logistic regression model. We haven't told it like what's in it, right? And if we just look at this model and technically in tidy models there's a function called translate. You can see here it's literally just calling GLM, right? So tidy models isn't creating new statistical things. It's giving you a consistent interface to work with all of the other models. So if you've done statistics in R before, like yeah, LM, GLM take formula methods, but if you look at GLMNet, it takes what's known as like model matrix objects, right? And so some things take matrices, some things take formula, some things take this. There's many different random forest libraries. They all work differently. Some have different parameters than the other. Really hard to figure out what's going on. Tidy Models tries to make that as consistent as possible. So it's like a one-stop shop to all of the stats that you want to do, including machine learning predictive models. Okay, so how do we go and use tidy models to fit a logistic regression model? So we have this logistic regression model. We pass this model into a function called fit, and then that's it, right? So I can literally copy and paste everything up here, paste it here. There it is. It fit our logistic regression model, right? So we no longer need to remember GLM. We can use logistic regression. And the reason for that is there are other libraries that implement logistic regression. Like what happens, like, a lot of neural nets like is really just logistic regression, right? But you can use a neural network backend to do the logistic regression calculation instead of regular GLM, right? And you can change that. And that's the benefit of using tidy models is it knows you're trying to do logistic regression. You can specify how it works under the hood. In this case, by default, it's using GLM. And then here's the formula, and it knows how to deal with all of the different ways it can make this calculation. And so given this, we can keep doing this just like normal, like before. Pass it into the tidy function in Broom, and then mutate the odds ratio is the exponentiate of the column called estimate. Right? So no difference there. And I really hope that the coefficients came out to be the same now that I'm staring at this. So let me prove that to myself. Yes, these values are the same. They're even the same decimal points. Why? Because under the hood, it literally called the same function. Okay, cool. So that's tidy models. So let's talk a little bit more about how this all relates to machine learning. Machine learning, again, my main concern, and this comes from Allison Hill's RStudioConf workshop from 2020, like literally right before the pandemic. I'm really just borrowing her slides. I feel a little bit okay with it because I was a TA for this workshop as well, so I feel okay like borrowing it from her in this manner. But let's talk about machine learning. So on the left-hand side, right, we want to be able to fit a model, right? Our model has coefficients and ways we can interpret the model and predict on you and interpret the model. What we are most concerned with is if a brand new person comes into the hospital or a brand new observation we've never seen before, we want to see how well it does, right? So this is known as like creating a predictive model. In our current case, logistic regression is known as a supervised model because typically we might already know the person's status. Like, oh, this person had cancer. Okay. How does our model predict this person who has cancer who just came into our wing, right? Our department. So we have this problem where we want to create a prediction, right? So how do we predict on new data if we don't have new data, right? Like if we just spent like $1 million running this study to collect data, there's no way. How do we like figure out if this is a model that's working okay or like performing well without spending another $1 million to collect new data, right? Like that's not a good business model or research model. So let's see, let's make a prediction, right? So we have our blood data set. I'm going to use the sample n function in dplyr. I'm going to take a random sample of 10 values in this data set, right? And so let's save this blood underscore sample. So that's our 10 randomly sampled data sets, right? So let's say this is how I created my quote unquote new data, or like I fit a model and then see how the model works on this random sample, right? So one, this is not the way to do it, but I'll show you the mechanics of how to run a prediction. There's a function in R called predict. And if you give it an object, a model object, so what is the model object? So let's, right here, this is the fitted model, right? So just right here, this is the model fit, right? So this is our logistic regression model that we just fit. If we put that as the model, and then we give it quote unquote brand new data, it will give us the predicted values, right? And this is, what is this representing? This represents the values for recurrence. It knows recurrence is the variable of interest, or the outcome variable. So this is the prediction of that. So we can literally compare, how does the predicted value compare with the original ones, right? And there's a few things to note around this data set. One, if you remember from this data set, there's a huge class imbalance problem in this particular data set. I think I can pass this into bar. Anyway, so right? So there's a huge class imbalance problem in our data set. Of all of our patients, we have 262 that have no recurrence, and we have 54 that do, right? So that's around like 80%. And so we don't know if this is a good model. First of all, you'll see that pretty much all of these values are 0, right? So if I had this model and it did nothing but just say zeros across everything, it'd still come back as like a model that's 80% effective, like quote unquote effective. Like that's not good, right? It may look good, but we know that this model's not doing anything. And this is a problem of our underlying data because this what's known as class imbalance. That's problem number one, why the values here are not something, why the predictive value here is not something you want to actually use. The other reason why the predictive value here is not what we want to use is because those randomly 10 sample data sets, we essentially are double dipping when we're doing the analysis. So what does that mean? I already used the data to fit the model, and now I'm using the model that I used on the data that I just like used to fit the model to predict itself, right? So it's not really new data. So even if this was like a problem that didn't have class imbalance, the results are going to be better than they actually are because it's predicting on stuff it's already seen. It's not brand new data, right? And so this is another thing that you have to be very mindful of, right? And this is, this is more machine learning theory and concepts and how you do modeling, but it has nothing to do with the code, right? Because you can see here the code worked. I can give you a prediction for whatever value 10. Was it a good one? I don't know. I guess it was also wrong because it's just predicting zeros, right? So the code, the fact that code didn't error doesn't mean like your model is correct, right? So when I talk about like here's the code to fit the model, like you can already see like I'm already writing more code just to make sure that this model is correct, right? I have to make sure that there's no class imbalance. I have to make sure that the predictions are right. Now I need to make sure and compare them and see the percentages, right? So there's a lot of other things you need to do, but these are all things that you have to worry about when you're fitting models. Class imbalance is one potential problem. You also have to think about how is this data collected, right? There's a lot of ethical issues around like is policing data we should really be fitting models around, especially predictive models where we can't make inferences from, because we know that there's a huge problem with the data set that's being collected. Like no amount of quote unquote good machine learning can fix that. So yeah, your code will run, your model will be there, you can go implement it, but it's gonna make your problem worse, or you're gonna perpetuate an underlying social issue, or et cetera, et cetera. All right, so we can't. So now the question is, how do we go and make new, like, how do we fake new data? Well, there's this step that we do in machine learning called the splitting step, where you take instead of sampling your data after you fit the model, you sample your data before you fit the model, right? So you take your original data set, You split it into what's known as a training set, the model, the data that you use to train, and then another set, typically called a test set. Like after you've trained the model and you fit the model, you want to test it on new data. And then you can get a better sense of whether or not this model performs well to new data. Well, performing well to new data, like it's always like the question of like relative to what, right? So it doesn't make sense to have one model and be like, this works well. It's like relative to what, right? Like the 80%, because of class imbalance, is like, oh, it's 80%. It's like relative to what? It's like it's already 80% if you just guess zero. So it's actually like not really good, right? Maybe it's better than like a random thing that's 50, but like that's just a terrible model because now you're just going from 80% to 50. So that's what tidy models also allows us to do, is to very quickly use the same formula or the same model with different formulas and just try a whole bunch of models together and then spit you out a whole bunch of results, and then you get to pick. So that's how tidy models is set up. So the first problem we need to fix is we want to fit our model on a training set and create a separate test set. Because it's random, we can set a seed so it's not as random, or you can leave it alone. But if you want the same exact values that I'm working with or consistent values, you can set a seed. And the function within tidy models that does the splitting is called initial split. We give it the data set, and then we can pass in a proportion. It's blood, not food. All right, cool. So this gives us the splits of our data. The proportion allows us to specify how much of the data we keep for training. So 80% we're keeping for training, and it's going to randomly sample out 20% for testing. The problem here is because we have massive class imbalance, right? Like literally 20% of our data is recurrent. There is a chance, and a pretty high chance, there's a chance that if we just randomly split our data, we're gonna end up with a test set with no one's gonna have a recurrent value, and that model is just gonna predict, well, everyone is a zero, so it doesn't even matter, right? So because we have class imbalance, there's another parameter you can put in, which is the strata parameter. And what this does is it will sample 80% of the zeros and put it into the training set, and then 80% of the ones and put that into your training set. So now you are at least, your splits have the same proportion of your original data set. And so that's what strata gives you. And you can put in multiple variables if you have multiple stratas, but you have to be careful that you don't end up with a data set with like one row. But that's what you can do. And this is because, again, we have massive amounts of class imbalance in our data set. All right, so now that we've done this split in our data, how do we go and access the training data set and a test data set? So we have blood train is equal to, there's a function called training. And if we give it this split information, you'll see here, it created a training set of 252 observations with 20 variables. And then we can do the same thing, if I spelled it correctly, blood test is testing of blood split. And now we have 64 observation with 20 variables. So now I go through the same exact process, but instead of fitting it on blood, I fit it on blood train. So I'm gonna come up here. I am going to copy paste this little part of the model. And all I need to do here is, instead of saying fit this model on blood, so I'm going to create the, sorry, give me 1 second. I don't mean to be jumping around, but this is the actual full part of the code. So we're gonna create a logistic regression model. We're gonna take this model and we're gonna pass in the training data set. And we have a model. And then we can do the same thing as before. So model fit, broom tidy, mutate, the odds ratio is the exponentiation of estimate. Right? And you'll notice one thing, like these coefficients are a little bit different, and it's because it's different, you expect it because the data set that it used to fit is different, right? Because we took out 20% that it didn't know about. The benefit of this is now we have a fitted model, right? We can run predict on that model. And then what is the data we want to pass in? Well, instead of training, it's test. And now you'll see we are now working with predicting test sets. Right? So one thing you'll notice here, because of our class imbalance problem, it literally predicted everyone as 0. Right? So we need a way to deal with this class imbalance issue, right? It's still like, yeah, we're correctly doing the prediction bit, but there's this class imbalance that we can't avoid, right? And that's because it's just, this happens a lot. Like in medical cases, you have rare diseases. Like you're not gonna find 1,000 people with this disease in your hospital, right? It's a rare disease. So like class imbalance happens in the medical context a lot just because you're dealing with rare diseases. And that's why rare disease research is so difficult, because these models, it's very easy for it to go, no, this person doesn't have like that rare disease, right? Okay. So before we go on dealing with this class imbalance problem, let's work out some of the mechanics of doing the model evaluation, right? If we take this predict statement, right, so that it calculated a bunch of predictions, and we can actually save this to a variable. So we have this predict op thing. So it's just a data frame, and it's a data frame with a column that's just called .pred class, right? So it's a regular data set. We can export this out. If you've done Kaggle competitions in the past, like this is what you export out and upload to Kaggle. So we have this predict function. I'm going to call this underscore class. What we can do is, this is the class prediction. What is a class? What is the category that it fits in? This is logistic regression, so the class can only be 0 and 1, but you can have other types of models that can predict like 0, 1, and 2, or whatever. So depending on your model, this output variable can be different. In logistic regression, it's just 0 and 1, and those are the classes that we can have. Another way we can use predict is if we pass in the parameter type equals prob, and not call it class, I call this prob. We actually get probabilities for each class, right? So this is saying, like, for observation 1, the model thinks it's 95% confident that it's a class 0, and then 80% is class 0, and et cetera, et cetera, et cetera. And maybe we can get like a good histogram or something. We can compare like, yeah, there's going to be cases where it's like really close to 50. So essentially the heuristic being used is, well, if it's 50%, if it's more than 50% in any class, then treat it as that class. So that's how the class predictions work. But if you want to break it down a little bit more, we can get the individual probabilities that it's filtering in. Why does that matter? Well, that's because we can change the cutoff point, right? Like, we don't have to use 50% as the cutoff. We can use other cutoffs. And that's where something like receiver operator curves come in, because you can change like the cutoff and see how the cutoff changes improve your model or not. But by default, 50% is going to be the cutoff, and that makes sense conceptually. All right, so we can actually take these all of this prediction information and put it together in one big data set. So we have a whole column that is the class probabilities, a whole two columns that are the prediction probabilities, but then we also have the column that's like the correct answer, right? So let's put all of that into a single data set. In tidyverse, there's a function called bind columns, and so that's what we can do. We have model predict class. We're gonna stick it on with the probabilities, and then I also want to tack on the blood testing the correct answer for recurrence. So we now have a nice little data set of what the model predicted, what the model probabilities are, and then what the actual correct solution is. Why is this important? Well, literally, we can take this set of results, and I think it's tally. Whatever this column ends up being. Give me one. It's called .4 in this case, and that's part of it is because my code is like a little wonky. But you can see here the predicted class of 0 and the correct class of 0, it gave 1, but the predicted class of 0 where the correct solution is 1 is 10. So it's missing like 10 of these values, right? And so that's not good. And we want a way to fix that. The correct way to write this so it's not as like terrible, I think I can just pass this into, yeah, so we can use the select function in R to give us a data frame, blood test. Yeah, I think this will fix it. Yeah, so now we have like the thing called recurrence. Right? So we want to be able to like tabulate how wrong how wrong this thing ends up being, right? And that's looking at, you might have heard of something called a confusion matrix. So what we did was literally create a confusion matrix. So in tidy models, there's a function called confmat for confusion matrix. We give it the data set, so this whole data set of predicted class, probabilities, whatever. If we say, what is the column that represents the true value? That is the recurrence column. What is the column that is representing the model estimate? Well, it's called .pred class, so we can say .pred_class. And here we get the confusion matrix. So you can see it got 52 of the observations correct and 10 of them wrong. How wrong or where was the incorrect portion of it? That goes into like type 1 error, type 2 error. There's a whole bunch of ways we can view that. I'm going to copy and paste the code because I can very quickly talk about it. There's different measurements like accuracy, sensitivity, specificity, precision, recall. They all work very similar to confusion matrix. You give it that whole data set of the class probability, the class prediction, and the individual probabilities with the correct the truth, and it will calculate, and it will essentially do different parts of the 2x2 table from the confusion matrix to tell you like where the mistakes are. So like one of these mistakes here, like right here, is like specificity. This is literally telling me that like it's getting none of the correct answers, like the one cases, like correct, right? Because it's essentially just saying it's all predicting zeros. Like this model is like awful, right? It's not very useful, right? But it's also saying like the sensitivity is really high because like everything that it did predict as zero, it predicted correctly, but it's like getting everything else wrong. And so you use a combination of all of these model metrics. One, you need to calculate it for a single model, but you use a combination of them to compare it to another model you fit. So you go through another process. Maybe you add more variables, maybe you pull out variables, maybe you put in interaction terms, who knows? And then you see, does that part of the model improve these model metrics? And there's a way to create it all in one nice little data set for you. So there's a function called metric set, and you literally list like what are the metrics you want. So in here you can put in like sensitivity, specificity, like stuff like root mean squared error doesn't make sense in this case. So yeah, like these things have to be like pertinent to the model that you're working with. But you can now get away with like here's the specificity, sensitivity, specificity, precision, recall. You can get all of that again in a single table, and that's probably something if you're doing like machine learning research. Maybe that's what you publish in your paper. Maybe you send that off to someone else, but at least you have a nice little data frame for it. One last thing, like I want to show, there is a metric called ROC, area under the curve, works the exact same way, and it gives you the ROC value. You can see it's less than 0.5, so essentially it says like whatever the model tells you, like just predict the opposite. Although I don't know if that's totally correct now that I'm looking at that. Oh yeah. I was predicting on the wrong thing. Yeah, there we go. So yeah, I was predicting on ones, and it's like, oh, if you do predict one, just predict the zero. But this is like the ROC curve, and if you've ever seen receiver operated curves before, like this is awful. Like I've almost never seen it like go below the dotted line before. But you can use this as like where should my cutoff be instead of just 50%. But you'll also see like again, this is not a very good model. But we already know this is not a good model because of class imbalance, right? And it's not able to handle the the like rare events. All right, so now let's go through, let's talk about other ways we can process this data. So we have our data set, our blood data set. It's in tidy format, and for time's sake, I'm going to go through this a little bit quickly. So just so we have this on record, I'll sort of rerun the original code. So we're gonna re-clean up the data set. We're gonna turn our response variable into a factor. We're gonna do our train test split. It's probably gonna be a little bit different because of the randomization. But in tidy models, there is this notion of, there's this package called recipes. Whoops, where's the picture? Uh-oh, hold on. I lost the picture. There was a slide with a really good picture, and I think I lost it. Hold on, give me one sec. Oh, sorry, it's literally on the next slide of this. All right, so this is the model process, right? We split our data. We then want to run what's called recipes on our data. Why do we care about recipes? Well, let's say we want to center or scale, like take the z-score of a column, right? Well, when we take our model and we say like, hey, predict your model on this new set of data, well, we want the same data processing steps. We see the same, like we want to do the same data processing steps on the new trained data, right? Like we don't want to be like, oh, I centered and scaled the data in the training data, but then I got new data and I didn't center and scale it. So the model's going to interpret the model. One, might not work, but two, it's reading in as wrong input, so the output is definitely not something you want to work with. So that's another like mechanic that your code is not going to tell you. You have to know to deal with it. So recipes is the library that says, okay, I know you're going to do a whole bunch of these like data processing, also known as feature engineering, like steps. So we're going to take all those cleaning steps, do it to the training model. We're going to save it so we automatically run the same cleaning steps to the test data set. And so that's where recipes come in. So what is an example recipe? So I'm going to copy and paste this for time's sake. Also because I am tired from typing. I'm sure everyone, you're definitely tired from typing if you're following along. But so we can create a recipe. The recipe looks exactly the same as fitting the model. We put in the formula. So these are all the variables that we want, and we can change and add them, do whatever. We're running it off of the training data. And then remember, like, I can turn a bunch of columns into categorical variables, right? Like, this is a step that I want to do for my training set and my test set, not just on my training set. So in recipes, there's a function called step underscore, and then a whole bunch of things. So there's step underscore mutate. You can manually create dummy variables. So there's step dummies. You don't have to specify the individual columns. You can literally say if it is a nominal predictor, automatically create the dummy variable, right? So it knows how to do that. In recipes, another pre-processing step that you would do is, let's say you're given a value and all of the values in that data is like a 0 or a 1 or like essentially the same value. In statistical language, that observation has 0 variance. And so there's literally a step that says, hey, if the data set has if the observation has 0 variance, just drop it. Like, it's not contributing to my data set. Like, just get rid of it. So there's a whole family of step functions. And all you need to do is I hope I'm still here. Anyway, all you need to do is Google. Don't Google just recipes. Like, that's what I've done like over and over the last 2 days. So if you Google recipes with tidy models, you'll get to the recipes page. Hold on. Yeah, sorry. Function reference for recipes. And if you scroll down, you'll see like step whatever. So you can put an imputation thing, so you don't have to manually impute. You want to run it in a step function. Why do you want to do all of this stuff as a recipe and not say like, oh, if I'm going to center and scale my data, let me do that before my training and test split? Well, if we go back to the diagram, the problem if we do that is if I did my imputation or if I did my centering scaling, well, centering and scaling and imputation typically requires that whole column of data. So that new data set that I'm going to split and test on later, a lot of that imputation information was used to impute the training data set. So it's no longer brand new data, right? So that's why recipes is set up in such a way where it helps you help you by not making that mistake, right? Because if you've programmed in R before this whole magical world of tidy models, that was one thing you have to be very mindful of is like, yes, I know I need to split my data. I also have to clean my data for a whole bunch of other reasons. What happens if you do the imputation step in the wrong process, right? Your code is not going to tell you where things went wrong. Right, so you can impute, you can do transformations, box cocks, you can like take logs of things. So some of these doesn't matter if you do it before and after training or testing, but this gives you a system where you can define the recipe all in one go. So you can convert things into dummy variables. So like literally look at this page, look for step underscore, and it can do things for you. Like you can literally like just get the PCA of your data set, right? You don't have to calculate PCA before your training, testing, splitting. you can just put it all in a recipe and it will do it all for you. One of the steps that I'm going to show you comes from this package called Themis or Themis. I think it's Themis. And there's a couple ways we can do with this class imbalance problem, right? You can see like this model is god awful. And how do we deal with rare events? So there's a couple ways we can deal with rare events, right? So let's say I have 100 people, 90 of them has no cancer, and 10 of them do have cancer. So we can do what's known as downsampling, which is literally take that 90, turn it into 10, but randomly sample that 90 to make 10, and now we have an even amount of people without cancer and people with cancer, right? So that's downsampling. The other way is upsampling, which is we keep the 90 observations that don't have cancer, and we duplicate the 10 until it's equal to the other group, right? So now we have 180 observations. And this is to boost the signal of our rare events. You can do a combination of them. So maybe you, instead of bringing it down to 10, you pick like a middle ground, like 50 or something, right? There's also another technique where you are going to like you use the data in your training set to make up fake observations to boost the signal. So there's a whole bunch of ways you can deal with class imbalance. I'm going to say downsample on recurrence, right? So give me the same number as like the 20% for in the recurrence group. So that's downsampling. So this is our recipe. It runs very fast because all it does is it's keeping track of all of the operations it needs to do. It hasn't done any work yet. How do we use this recipe? Here's another copy and paste block of code, and I'll talk through it. We set our logistic regression. That part is the same. We then put it into a workflow. In this workflow, we can put in the model, put in the recipe, and this gives us inputs for trying out different recipes, different models. It can all be into the one giant workflow, and then we can calculate a whole bunch of different models at the same time. In this case, I'm only using one, and then everything else is the same. We can fit our logistic regression, and then we can predict, and essentially one of these, I think like upsampling was the one that like performed better or something. But now you have a mechanism to try out a whole bunch of models and then compare them to one another. So that's it for time. I'll post all of this stuff like very, very soon, but I wanted to sort of talk through less about like tidy models, like the actual code, but like tidy models is a way for you to not make modeling mistakes. And I really wanted to emphasize more on like the potential mistakes you can make. But yeah, so with that, that is time. And I guess what we can do as everyone sort of logs off or heads out. There's, I guess, just one slide or really two slides from part one that I kind of want to go over. And it's mainly the resources that you can use in the R community. So let me go and point back to this. So there's the R4DS book. We went through the same concept. So hopefully you can use this as a pivot point to learn more in the R4DS book. The R4DS book isn't medically oriented, but you can read the two together to see how things communicate. The R4DS community is a Slack group. There's literally office hours. If you need help, you can go there and like call in. They're going through the tidy modeling with R book as a book club if you want to read along that. There's a resource called Big Book of R with a bunch of other R free resources. If you want data sets to practice, there's Tidy Tuesday. David Robinson and Jesse Mostopak both stream how they process brand new data sets, and you can see a lot of the tools at work. If you identify as a lady, there is the R Ladies Slack group, where you can also use another resource to help you with any of your R coding problems. And then since this is about our medicine, there's also an our medicine conference and Slack group as well. And for those of you at Virginia Tech, Anne and I are here at Data Services, somewhere along the internet. Alex Hanlon's group she runs the Center of Biostatistics and Health Data Science. Literally, if I was teaching in person on the same floor as I would have been teaching, and they literally have drop-in consulting hours that you can go in for help if you're at Virginia Tech. So you can hit them up as well. From the carpentry side, there are other tutorials. Someone the other day talked about like they do a lot of image analysis, so you can look at the carpentry's materials for something that's more domain specific to your own work. And then last but not least, if you're still here, please let me know by filling out the post-workshop survey. And that will be really helpful for me improving improving the content that this set of materials is coming out of. All right, so with that, I will sort of just conclude everything. I'll sort of stick around a little bit until everyone roughly leaves the Zoom room, and I will figure out what else is going on the other side. I believe on the Twitch side, Lisa is streaming, so we can move over there to her side. But yeah, with that, I will sort of conclude this class, and we'll sort of hang around, and I'll get all of the materials out shortly.